Okay, so we were discussing about the we just started the discussion about the bus in the 2 to 3 class. Now let me ask, any of you have any query regarding what we discussed in the 2 to 3 class? Because I could not answer question it then. So do any of you have any question regarding the discussion of 2 to 3 class? Then we'll start. Uh, then we'll continue from what we discussed in that class. Okay, so instruction pointer, as you can remember that what I discussed in the previous class, that instruction pointer holds the address of the next instruction to execute. That means whenever the operating system brings the application into the RAM, it informs the processor that yes, the application is loaded at this address, start executing from this address. That's it. So now there are several things come in between. As I said, address bus is used to take the address from the CPU to RAM or all those devices which holds data like video card, that means dedicated video graphics card, and so on. Now let me, for the simplicity, will consider only about the relationship between the RAM, processor, and the hard disk. Um, Here, once the application has come from hard disk to RAM, uh, we can simply cross this part. So it's now only between RAM and CPU. Though in originality, hard disk also plays in action, but we'll not go into that level of details. Now, once the application has been loaded, the instruction pointer is also loaded with the address of the first instruction. So the CPU on its next cycle means, if you can remember, I discussed about a concept of clock. Everything within a computer is synchronized with a clock signal. The clock signal, in fact, is a periodic signal, something like this. Right? And it generates at a particular frequency. As for example, it generates at a particular frequency. Now, if you have, I think you have also heard that CPU is 2.9 gigahertz CPU or 3.7 gigahertz CPU and so on. That means if I say that say a CPU is, say, example, CPU is 3.7 gigahertz, that means it can work with a clock signal uh, that has the frequency of 3.7 gigahertz. That means uh, I think you know the definition of frequency. That means at a particular, if you take a particular location, the number of signal, say one particular point of the signal, that is this particular point, how many times it is passing through that particular location or something like that. In short, how many these signal is passing through a particular location, or in other words, if your CPU is 3.67 gigahertz, that means your CPU per second, right? The CPU per second can accept up to 3.7 into 1000. Here 1024 is not used. It makes as megahertz, kilohertz into this many number of. Just one second. I have. Just wait for a few minutes. Okay, so sorry for the interruption. So what I was saying is that it can work with a clock signal that has this many number of waveforms uh, on which CPU can work. Waveforms per second. On which CPU can work. Now, where do this this clock signal comes handy? As for example, let me give you an example. Everything is synchronized on clock signal means, as for example, now it depends from architecture to architecture. Maybe some CPU can be synchronized on when the clock is going from low to high. This is called rising edge, right? So some operation is going to happen at each rising edge of the clock, or maybe some operation, maybe some computer can be programmed or can be designed, in fact, rather than saying programmed, to work on the falling edge of the clock. This is called the falling edge, that is going from high to low. Now, for our ease of discussion, we will consider any one of them, say rising edge. Now, that means every operation happens at rising edge, or as I've said, it depends upon, or maybe the falling edge of the clock signal. Now, why this synchronization is necessary? Let me give you an example. Suppose you have this RAM. Try to understand this example because you'll understand why synchronization is necessary in a computer system. Suppose the address is coming over the address bus. Okay, suppose this is the address bus. and this address has been generated from the instruction pointer register. That is coming to the RAM. What RAM will do? RAM will simply look for what information it has at that address and will send that address over the data bus. So CPU sends address over address bus. RAM returns the information at that address over the data bus. So there is a data bus that is going from RAM towards the CPU. Now, if you can see, I have kept a place. In fact, there was also a place. I'll remove this here. Now, what the problem happens? Consider this scenario carefully. Suppose, example, CPU. Suppose I'm considering about, say, an 8-bit system. Okay, and a very old 8-bit system. So addresses are of 8 bits. The data that is coming are also 8 bits, and so on. Suppose CPU has requested information from address, say, let me take any hypothetical address 01101011. Okay, from this address, today's address is 64 bits. I am considering an 8-bit system. CPU has requested information from this address. Now, address bus in today's machine is of 64 bits, but originally there are 8 lines. So there are 8, in fact, we call lines, but let me write it so that you can understand for now. There are 8 wires that is carrying the signal. Remember, the bus is nothing but a group of wires. So address bus, it is a unidirectional. The signal can go only in one direction. Okay, that can be controlled using proper electronic device, and that address that and the signals on that address bus will go based upon what address you are sending. So as for example, if it is 0110101, so among these 8 bits on the second, third, fifth, sixth, and second, third, fifth, seventh, and eighth, these 5 lines will be high. The rest of the 3 lines will pass low voltage. Now, these are physical wires, right? There can be delay in somewhere. It's not that all wires are of same speed. They can take the data to the same speed. Delay happens within the circuit. So this is one very important fact you must understand. Delay happens within a circuit. Though the delay is not much, even at the level of picoseconds, but it's lower than nanoseconds. But delay happens. Don't think that these 8 bits will be fed to the address over the address bus at the same time to the memory. No, that will not happen. Now, what if among these 5 bits, maybe the delay is on this line? Suppose the delay is on this line. So, what address memory will see? Anyone? If there is a delay on this line, so this signal will reach later. Whereas previously this 0110, now this signal has not reached till now, so it is 0 still there. So 011000011. This is the address that the memory will see. And just afterwards, after that particular picoseconds, memory will see the address 00001000. Have you understood what I said?
Yes, sir.
Okay. Now that's where the problem is.
Sir,
So bolo.
you said this happens in the circuit itself, right, sir?
Yes, itself. It happens
Sir,
itself.
can we make it intentionally? I mean, uh,
Obviously, you can make it intentionally. Make some make some loop within the circuit. Okay,
okay,
or make some or put some device that leaves the signal unchanged while operating in the device. A delay will happen. Okay,
okay, sir.
so it can be made intentionally as well, but generally it automatically happens. So to avoid this problem, a register is kept near the memory. That is called memory address register. Okay, so when CPU sends address, it first comes to memory address register, MAR. Okay, so think the register like this. The address, say this 4-bit address has appeared, but clock signal has not been appeared till now. That means so on the output lines it is still 0. Memory still knows that no address has been sent till now. Only when the rising edge of the clock will occur, as for example you have considered the machine that works on rising edge, only when the rising edge of the clock will occur, then the memory will see the address coming out of the, because this q0 q1, there will be the output from the register, that means output from the memory address register, each line. It is only when the rising edge of the clock signal occur, the memory will see the address. Now if delay happens in some bit, does not matter, because the address, whenever the CPU released the address, it did not come immediately to memory. While the other bits were waiting on the other lines, uh, as the delay happens only in picoseconds, even lower than nanoseconds. By the time next clock edge arrives, uh, the other bits have also appeared by then, and at the particular clock edge, at particular clock signal, all bits go to RAM together. Okay, so this is the importance of synchronization. Without synchronization, if there would be no synchronization, your computer would not work so reliably. Though today's modern circuit researches are happening on even designing asynchronous circuits, but they are even more complex. Several things are being brought together to keep the data intact without clock signal, but that's still at the research level. So this is, so in our basic, the computer still we are using, they are using these registers and clock signal so that uh, no mismatch in the information happens. Okay, so the address first comes to this. So now let me update this image a bit. So the address comes to the memory address register, then from the memory address register it goes together to the RAM. It is just close to RAM, no delay happens in any of the bits. All the bits can reach to the RAM directly, safely. Okay, so this is how information is synchronized within a computer, and that's why everything happens so perfectly within a computer, just because everything happens at one particular instant of clock signal. Is it clear?
Yes, sir.
Okay.
Yes, sir.
Okay. Similarly, when the RAM sees the address, I'll not discuss about this architecture for long, don't worry. This data will go, right? Similarly, when the data will go uh, of how many bytes together there is in one row, because today's RAM information go in 8 bytes together, that means 64 bits together at once. All the 8 bytes go at once. Okay, so depending upon that, these 64 bits, or if we consider our 8-bit machine scenario, these 8 bits will come out of the data bus, and this data bus, it will not go directly to the control unit, rather it will come to a register. Though this register stays closer to the control unit, in fact closer to the CPU, this is called memory buffer register, that works as a buffer. That means a temporary storage for the data is memory address register, and this is memory buffer register. Okay, so in a sense, what I can summarize is that when some instruction needs to be executed, the processor sends the address that is currently in the instruction pointer. That address goes over to the address bus, and it comes to the memory address register, waits for the next clock signal. At the immediate next clock signal, it is that address completely is fed to the memory. RAM uh, looks into at what address, from which address it wants the data. Okay, from that data is sent over the data bus. This is data bus, which is also, after being brought, is kept into another register, memory buffer register, temporarily, which at the next clock signal, this is clock signal, which is driving both memory address register, memory buffer register, and everything else in the system. Okay, so that then it gets synchronized into the memory buffer register, that data, and then it is brought to the control unit. control unit decodes. That means control unit, after watching the instruction, it understands what to do and it sends the corresponding signal to all the peripheral devices, including ALU. If RAM needs to be accessed again, to the RAM, the monitor, keyboard, wherever it needs to be sent, to all the ports of your device all over the motherboard based upon the instruction. Okay, so that's how everything happens within the computer so reliably. Okay, now any question or any confusion till now?
Sir,
Bolo.
sir, can you say about that clock speed, how it actually makes a CPU works efficient?
Okay, generally this clock it is generated using the vibration of an atom, generally some crystal atom. Okay, and from that vibration the clock signal appears. Now it is also kept on the motherboard. Now don't think that the clock on the motherboard is if you open up the motherboard, in the old motherboards you'll see a battery. Okay, this clock, the battery of that clock has nothing to do with the clock you see. First of all, the battery you see on the motherboard, it keeps your system clock on. Okay, that means the time, that keeps the time on even after you power off the computer. Okay, whereas this clock is entirely something different. This clock is simply a signal, nothing more than that. It has just been named clock. Okay, now as the clock signal gets generated, now this clock also comes to the CPU as well. As an example, now the control unit, as an example, control unit is a completely synchronous device, as I've told previously. That means everything in the control unit, all the signals that it is going outside, it is taking the instruction into the instruction that is going into the control unit. Everything is happening at the appearance of the clock signal, right? Now suppose at the next clock edge, that means the rising edge, because we are considering the rising edge computer. Suppose at the next clock edge, the signal, suppose the instruction has appeared something like, say there are multiple registers here. Say there are two registers. I'll tell about these registers in details, don't worry. Suppose RAX, RBX, and my next instruction is say add RAX, RBX. Okay, what will happen when this clock signal will appear? That, sorry, clock signal, not clock signal. The control unit will decode the instruction, will send the signal, but those signal will also be sent at the next clock edge, not before, not after. Exactly at the clock edge, the signals will go out of the control unit. Now, so at the particular clock edge, the signal comes to both RX and RBX that release the data. They release the data here, and again it is waiting here. Don't think that it is fed. Let me draw it a bit bigger. Control unit is somewhere else who has sent the signal at the clock edge. Now this is the ALU. Suppose this is the adder. This is the adder symbol is used in architecture. The adder that I have shown you. Now this information together at the clock edge. This information comes out of at the clock edge. The clock edge when when the controller sends the clock signal sends the corresponding signal. It again comes stored into a buffer just prior to the ALU. Just prior to the ALU, it gets stored into the buffer. It does not go to the ALU. Just again at the immediate next clock edge, all the bits will be fed to the ALU together. Otherwise, what will happen? Maybe the information from RX came first, RBX made some delay in reaching there. The information, the data from RBX made some delay in reaching there. Obviously, what will happen? The output of the adder will only be the RAX plus 0, the information of RAX plus 0. So that does not happen because the instruction I wanted was add RAX RBX. So the next clock signal, they will be added. Now the question is, everything has been kept at a particular. Now suppose that the clock signal is kept so high that it does not make any sense. Say the maximum delay. Try to understand. I'm trying to elaborate in a simpler language. Suppose the delay, maximum delay that can happen within the system, say is 2 picosecond. Okay. Now, suppose this is the maximum delay that can happen. Don't worry, this will not be in syllabus. Now, if two consecutive clock edges appear within 2 picosecond, consider this as something like this. RAX has come here. RBX is going to make a delay of 2 picosecond, but a clock edge has appeared. What will happen? Synchronization will simply not work, right? So the synchronization will not work. So in a sense that, see, I do not know how much delay occurs in today's i7. I have just taken this 2 picosecond as an example. So I think you have understood that you cannot just make as sufficiently
Yes,
high speed as possible.
I got it, sir. I got it.
Okay. So that's for clock signal, and that is the limitation of clock signal.
सर
हाँ बोलो.
सर क्या हर सिग्नल उसको एग्जीक्यूट करने से पहले वो एक रजिस्टर से पास होता है?
एक बफर से पास होता है. Buffer is also works like a register. So in a sense, yes.
Okay.
But we generally use the term registers in a sense which we can use. That I'll tell you. See, there are multiple registers in today's processors like i7 or so on. Among them, as for example, instruction pointer. It is an important register because it holds the previous address. But because these registers are meant to hold the data, meant to hold some particular information, some particular meaningful data, they are registers. Okay, where otherwise there are buffers all around to synchronize the signals, but they are just buffers. They do not hold any data particularly. They are just there to make the synchronization there. Right. So even though the design is same, we call them buffers, we call them registers. Registers are meaningful. Buffers are just a part to make the synchronization work. Okay. So as for example, there are 16 general purpose registers: RAX, RBX, RCX, RDX, and so on. Okay, they have been named, these 16 general purpose registers, but other than them, there are hundreds of registers which, as a normal programmer, we cannot access. We cannot access. As for example, this instruction pointer, we cannot access it. Okay, we cannot write our own choice of address to the instruction pointer. We cannot. Only these 16 general purpose registers, these are what we can control via programming. Okay, the rest of the hundreds of registers, therefore internal calculations of the CPU and operating system. Okay, now let's go to the next level of discussion.
Sir,
It is
sir,
bolo.
sir, what the register actually is?
Register is a storage. Register is a storage.
That means it is stores something, right?
Yes, it stores something. In fact, 60 general purpose register, they are all of 64 bits.
Okay.
All of them can hold 64-bit data. Remember the design, a rough design I have shown here. Each of them holds 1 bit. The bit I'm sending here, each of them holds it. Only at the particular clock signal, the output reflects what is held in that register. Okay.
But sir, you said buffer is also a register, but that doesn't store value, I think. Instruction, I mean.
As I said, buffers and registers, they are same in design. But
okay, same in design, just
yes,
okay.
same in design. But registers are those special purpose which holds something meaningful. Instruction pointer holds next address. RAX, RBX, RCS, they hold our data. These 16 registers, they hold our data. All the addition, subtraction, all operations you will do on these 16 registers. Okay. Then there are hundreds of registers. There are CR registers, RIP that holds the instruction that holds the top of the stack point. That means each register holds something meaningful. Whereas buffers, they are just intermediate temporary storage used for synchronization. Nothing more than that.
Right. Okay.
Another difference.
Okay.
Buffers are come and go. That means they are meant only for temporary storage. At the next clock signal, it should not be there. Whereas in the registers, it is our choice how long I'll keep the data there. Okay. Is it clear? So as for example, okay. So next phase of now, we'll look into the detail of what is happening inside. Before discussing this inside of a computer, let me discuss something interesting. Evolution of programming languages. See, when you will mix up the programming, in fact, in computer science, it is generally a very bad practice to always keep something like it is software, it is hardware, it is programming, it is architecture. Don't think like that. All of them are dependent on everyone. And once you know that complete course, starting from the architecture to the programming, you know and once you can know how to relate them, you know the core of computer science. Then, okay. So I'll come back to the I'll come back to the inside of computer again, but maybe I'll not get the time today after telling about the evolution of programming languages. See, the early programmers used to program in zeros and ones. That means which we call machine language. This is what we call machine language. So in at the time of when the first transistor, as for example, transistor was discovered in 1947. Yes, the same way the same year in which we got the independence. In 1947, transistor was invented. So though before that electronic based computer was there, though which used to use vacuum tubes, right? The size of even a small computer, maybe that means we'll say small computer in the sense that if you look into the evolution of computer, you'll see how everything has evolved at the speediest rate. Today we talk about RAMs, for example, 8 GB, 16 GB, even mobiles are coming with 8 GB of RAM, right? But even in 1992, when Linux was designed, even a computer with 4 MB of RAM used to be a very highly special computer. So you can think about so where it is going. So at the time of those 40s and 50s, the programmers of those era, they literally used to put the bits directly into the what is say today's memory. That I'm going to put 0 here, I'm going to put 1 here, put 0 here, and so on. A few bytes at most.
सर लीव कर गए क्या?
Okay, I just got network issue. Okay, my network got disconnected as current went off. Okay, so sorry for the interruption. Let me share the screen again. Well, so what I was saying is that so in the 1994 or 1990s era, even computers of 4 MB or 8 MB RAM was extremely great computers. So you can think at which speed the electronic devices are being developed. in the 1940s or 50s. So you can think that the programmers were able to put the bits themselves into the RAM slots, right? Which we in today's world obviously cannot even think about it. They used to put 0, 1, 1, 0 and so on. They, in fact, they used to uh, punch information on a they used to punch information. Is my screen shared? Okay.
Shared, sir.
Yes, sir.
Okay. They used to punch information on a punch card. That means where the punching would happen, maybe that would be 1, where there was no punching, that bit position would represent 0. Then they used to simply put that punch into the memory directly. Okay. Uh, Maybe the complete memory was of size a few bytes, but even that few bytes of memory designed using vacuum tubes would take the space of a complete a huge room. Okay. um, so in today's world, our jobs are extremely easy as compared to those 40s and 50s programmers, because they directly used to write the programs in terms of zeros and ones. So what they used to do, that means, as for example, they want to add say 3 and 5, they used to look into say uh, a chart, right? Chart where all the instructions and its corresponding bit patterns used to be written. Okay, they used to look into the charts and then used to simply punch the corresponding bits onto the punch card and put that into the RAM, that punch card. Then the computer used to execute that for days, and yes, days, not even hours. And yes, maybe very small programs would execute in hours, and then they used to come back and take the data in another punch card, right? So there was no keyboard, no memory, sorry, no keyboard, no mouse. Forget about mouse. Mouse is a very recent invention, because even in 1980s there was no GUI on computers. So
What
keyboard,
GUI, sir?
huh? The
What
graphical
GO?
the graphical user interface that you are seeing, you're taking the mouse around and clicking here and there. That is your GUI.
Okay.
Now, in today's world, we cannot think without this, right? But even in 80s, everything used to happen in some terminal writing commands. Okay, so that means if you say if you want to, in the next class, I'll show you from Linux, and I'll show you how commands used to be used at that era, and in the 80s. Maybe in the command, if you type say at that time there was no Firefox, maybe say dbase. Dbase was 80s era as a very famous database management system. Okay, uh, so they used to write say dbase, press enter, and database that used to be controllable only via keyboard, not mouse. There was no concept of mouse there that would open in front of you. Now, as I was saying, that in the 30s and 40s, there was no keyboard, mouse, or even monitor. Okay, they used to put the punch card there. Result used to come out in terms of some punch tapes or something else in terms of the tapes. So now think about this. They used to punch ones and zeros and so on, and operations used to happen in hours at least. So there used to be, it was not that on everyone's desk there used to be a computer. There used to be a single computer taking the whole room. programmers used to wait in front of the computer to wait for the punch, to give their punch card in line, maybe in a queue. If somehow someone's program faces an error, which was very common, think about it. If you need to write programs in terms of ones and zeros, I really doubt anyone in today's world will be able to write program perfectly. Okay, so at that era they used to punch them without even looking into any monitor. They put that. Now if some error used to happen, they used to be able to know that after hours or even days. And if some error happens, then that time got wasted from his or her life. So to overcome that situation, programmers, a bunch of programmers, what I can say, they beat the bullet and took a risky job. So a group of programmers created a software, created an application, and obviously this huge application was written completely in terms of zeros and ones. Created an application called assembler. That would take command in pure English language. By that time, the era of punch cards were also done. Keyboard was coming. A very small version of operating system has appeared in the world, and so on. That would take command in pure English language. But remember, they wrote this assembler in the terms of zeros and ones. It was an extremely difficult program, and they wrote it successfully. What this assembler do? Remember, in the punch card era, suppose if I want to add 5 and 6, or maybe add RAX and RBX, maybe in the machine language, that may be say 1 0 1 1. I'm just writing it for some hypothetical machine. Okay, maybe that's in machine language. What assembly language did is converted into add RAX RBX. That means add the content of the registers RAX and RBX. Okay, I'm using this dollar symbol as a symbol of register, but obviously the first assembler did not include this. In fact, there was no RAX or RBX at the time as well. There was only a few registers, one called accumulator and so on. Now, the assembly language would look like this. What assembler do is that it takes each of these language line by line. Suppose you are going to add RAX and RBX and store the result in say RCX. Then maybe you are going to subtract 5 directly from RCX and store the result in say RDX and so on. So this is the corresponding assembly instruction, assembly language program. What assembler does is it takes each line by line and converts into the corresponding machine instruction. I have just written the two hypothetical machine instruction for them. But the programmers of 40s and 50s at that era, they used to write directly in this on a punch cards. So assembly developers, assembly language developer created this program assembler that would take the instructions. These are the instructions in English like language. That means if you want to add, write add. If you want to subtract, write sub, and so on. And they used to convert that line by line into the machine language. Programming became very easy because at that time this was a huge achievement. Rather than remembering ones and zeros, now remembering them was much more easier. But as the program requirement grew,
Sir,
bolo.
sir, in this assembly, what are those add and sub? Are the functions?
No, there is no concept of there is a concept of function. In fact, it is called procedure. They are instructions. These are the instructions. Okay. So as for example, if you write add rx, rbx, rcx, here this instruction will tell the control unit that activate the adder, send the corresponding signals to adder, take the data from rx. Bolo. You understood, na?
No, sir.
Hello? Your voice is quite breaking. Hello? Can anyone kindly decode for me what he is saying? Well, so okay. So these instructions, they are simply instructions, not functions. These instructions are taken. In fact, if you write some program in assembly language, the assembler will convert these instructions. Today's computer still does everything in machine language. So don't think that your today's computer can see these add, sub, and so on. There is an assembler working that takes this assembly language and converts it into the machine language. That machine language, then instruction by instruction, this one instruction, instruction by instruction is then taken by the control unit. Control unit understands it and sends the suitable signals to all over the motherboard. Okay. As for example, if I write say in say some say CAB 5, that means take the and say I'm just writing a hypothetical value, say dollar or say $RX. That means take the data what has appeared in the port with address CAB5 and put that into RX register like this. Okay. Now, rather than going into the details, I think it's 5:59. But so I'll keep my discussion up to this today. Next day, but obviously, let me just give you a hint. Today, we use high-level programming languages because even using assembly languages, as more and more complex softwares, the demand of more and more complex programs appeared, even these assembly languages could not satisfy that. So today you use high-level programming languages. Okay, and a program that is called compiler. Compiler compiles the program in high-level language to program data in high level to assembly language.
Sir?
Bolo.
Sir, at that time at 19, for scientific and for scientific computing and numeric computing, are these same high level languages used, or any other languages are used?
No, there were in fact near the beginning of the 60s and at this era some programming came, like say Fortran, formula translation, basic, COBOL, but they were in fact somewhere between assembly language and today's high level language. Okay, so we can consider in fact Fortran was the first high level language, and this was the most common for scientific computation. That is called formula translation. This is Fortran. That was used for scientific computation.
So after this Fortran came, then Algol and COBOL came, sir.
In fact, truth to be told, in which sequence? Yes, Fortran was the first one. In which sequence they exactly appeared, I don't know. Maybe I can check it out. But Fortran, Algol, COBOL, Basic, they all appeared one after another. Okay, but
Okay, sir. Okay, sir.
they were between this assembly language and when the new era appeared in 1972 with the invention of C programming language by Dennis Ritchie. Okay, so C was designed by Dennis Ritchie and Brian Carnigham in 1972. As far as I can remember, it's 1972. Okay, and after C was designed, the completely new era came into the history of programming. So the golden era of programming started. What you are saying today, every programming you are writing in on your machine using C, Java, using Java, Python, C++, and so on, they all have taken the idea from C. In fact, the Fortran, COBOL, Basic, Pascal, these programs, though they were a bit higher than assembly, but still they were not what we call structured programming language. I'll tell you the difference between structured and unstructured programming language. They are not structured programming language, right? They used to use an instruction called goto. I'll tell you everything in details. What is the disadvantage of goto? What is structured programming language? When you'll start C, I'll discuss this in details. C was the first structured high-level programming language that simply changed the era of programming. And after that, this is where we are. And eventually, all the programs written in these high-level programming languages like C, Java, sorry, not Java completely, rather C, Rust. Today, in fact, interpreters are coming more than compilers, but I'll discuss about them later. Interpreter do not compile into assembly language, but the language that will study C, it is a compiled language. It compiles any program written in C language in the assembly language. That assembly language is assembled by a program called assembler into machine language. That machine language is then executed on your processor. Okay. Any of you have any query? Any of you have any query? Okay.
No, sir.
Okay. I'll discuss this
Thank you,
discussion.
sir.
Okay. Okay. Thank you. I'll discuss this
Can,
discussion to this today. We'll see you next week.
thank
Thank you, sir.
Welcome.
Thank you, sir.
Welcome.